Alright, so we're going to be a bit all over the place today. I want to finish 6.2. There's really just one more theorem left in the section. But then I want to talk about one of the problems from the section. Yeah, just one of the exercises at the end. I think it's sort of enlightening as to what's going on with the angle of parallelism. Then I'd like to talk a bit about the homework. So remind me if I forget to do that. And maybe then I've got this problem written down here about Lambert quadrilaterals. If we have time, we'll go through that. But in any case, here's the last theorem from the text in this section. Remember we were talking about the angle of parallelism in Euclidean versus hyperbolic geometry last time. This one really shores it up. So the theorem is that the Euclidean parallel postulate which is of course just Playfair's, postulate, same thing, is equivalent to the angle of parallelism, being 90 degrees. And of course, one direction this should be obvious. In Euclidean geometry, the angle of parallelism is 90 degrees. This sort of establishes the opposite too. If it is 90 degrees, then we're working with Euclidean geometry. Then we have the Euclidean parallel postulate. And I won't write this down right now, but this means if we go back to our list of growing things, we've got this long list of the following are equivalent things, right? We've got Euclid's fifth postulate, we've got the Euclidean parallel postulate, which is Playfair's. We've got what else? A rectangle exists. We've got the angle sum of all triangles is 180 degrees. We've got Pythagorean theorem. You can now add this to that list. So here's another entry in the following are equivalent. The angle of parallelism is 90 degrees for every line and point pair. And so my proof is really, it's not super formal. I'm tempted to call it a sketch. But the forward direction is immediate because we actually did this last time. Right? So at the end of last class, look back at your notes, what's the last thing we talked about? At the end of last class, we proved that if the angle of parallelism is less than 90 degrees, so at the end of last class we proved that if the angle of parallelism is less than 90, then there exists, we did 2, but then we showed that it's actually infinitely many, but that there exists more than one. Let me phrase it slightly differently. Then, given L and a point P, I really don't like the way I'm phrasing this. Let's get rid of a whole bunch of words. We prove that if, given L and a point P, if the angle of parallelism is less than 90, then there exists at least two lines through P that are parallel to L, right? Then there exist at least two lines through P parallel to L. Right, what were they? Well, we had the ray that actually sort of attained the angle of parallelism. Then we took the 90-degree ray, the perpendicular ray. There's two lines that are parallel to L. So there's at least two, and then we had in between them infinitely, uncountably many more. Why am I mentioning this? How does this relate to the statement at hand? Well, what does this say? If let's negate this statement. Right, so let's take the contrapositive rather, I should say. So this says, if the angle of parallelism is less than 90 degrees, then Playfair's is not true, right? Then not Playfair's, because the negation of Playfair's, Playfair says there's exactly one line parallel. The negation of Playfair's, we know we can't have less because there's always at least one. So the negation of Playfair says there's at least two. So this says, if the angle of parallelism is less than 90, then not Playfair's. So take the contrapositive. The contrapositive would be if Playfair's is true, then the negation of this. What's the negation of angle of parallelism is less than 90? Well, it can't be bigger than 90, so the negation is it equals 90. So this is just the contrapositive of exactly what we want to prove. Contrapositives are logically equivalent, so we're done. This is the contrapositive of the forward direction that we're trying to prove. So this is done. Again, as long as you're willing to accept some basic facts about the negations, right? Technically, if you just read this statement, the angle of parallelism is less than 90, the negation would be bigger than or equal to 90, right? But we know we can't be bigger, so the negation is technically just equals 90. So there's a contrapositive. What about the backwards direction? Again, this is where I say it's sort of a sketch. I'm really just going to draw a picture here, and the details are very obvious. So let L be any line and P any point not on L. Assume that the angle of parallelism is 90 degrees. And so we want to show if the angle of parallelism is 90 degrees, then given this line and point pair, there's exactly one line through P that's parallel to L. That's the Euclidean parallel postulate. And we'll just construct the same picture that we always construct. So construct the following as usual. I don't really like that I'm using construction language here. I'm not taking out a compass and straight edge and then doing this or anything, right? It's just we know all these things exist, so go through the existence process to show that we have all of the following. Here I've got Q and S, which is my line L. We'll toss in the perpendicular. Then I've got P, and we'll toss in the perpendicular here. These two lines are, of course, parallel. S prime and R prime. All right, so I've just got I've got two parallel lines and a perpendicular transversal. And I call this, call that line M. So if the angle of parallelism is 90 degrees, why is M the unique line? Well, if it's 90 degrees, then I can't have any semi-infinite rays like this that are parallel, right? And I also can't have any like this. Why not? Well, because if I try to extend this, well, I can't have a semi-infinite line that doesn't intersect, but if I try to extend this to a bi-infinite line, this would push over here, and over here, this would be less than the angle of parallelism, because the angle of parallelism on that side is also 90 degrees, right? So it's sort of a very obvious statement that I don't want to write down all of the details for, so we'll just, we'll say M is parallel to L, and angle QPR and angle QPR prime are the angles of parallelism. So M is, in fact, is the only line through P parallel to L. And in fact, I suppose that statement is totally fine. I'm not really writing a sketch. I just feel like I'm not going to write down a full justification of this statement. I'm leaving it to you, to the reader, to make sure you understand why that's true. I probably should justify it a little bit more. But do you believe me? Right, if this is the angle of parallelism, if 90 degrees is the angle of parallelism, then I can't have a line like this, because I'd be less than the angle of parallelism on this side, so I know it would intersect. And I can't have a line like this, because on this side I'm less than the angle of parallelism, so it's going to intersect. So that is the only one. Therefore, the Euclidean parallel postulate is true. And we've established the result. So we've got this long list of equivalent things. Here's another one, Euclidean parallel postulate, equivalent to Euclid's fifth postulate, equivalent to all these other things, but now equivalent to the angle of parallelism is 90 degrees for any line and point pair. But I want to think about what happens in the hyperbolic realm. Okay, can I erase this? Right, so this is obviously true in Euclidean geometry. You take a line, you take a perpendicular, you choose any point on here. Of course, if I make this angle anything less than 90, it's going to intersect. So the angle of parallelism is 90. But what about in the hyperbolic world? Let's let's go with the upper half plane model. So this is the upper half plane model. This is, of course, the x-axis, so plays the role of the boundary of infinity. And let's say I take one line. So one line is going to be this vertical line. And it's, what labels have I been using? I've been using Q and S, right? So here's Q, and here's S. So this is the line QS. And just remember, I'm building this picture again. We usually have Q, S, we put a perpendicular through it, then I've got P, and then I've got R. This is sort of our standard picture that I've been drawing for angular parallelism. So, and this is 90 degrees. So what I want is to QS in this picture. To QS, I want a perpendicular, the perpendicular through Q. How do I get the perpendicular through Q? Well, it's going to have to be perpendicular through Q. And what do lines look like? Well, if you're not these straight vertical lines, then the other straight lines in hyperbolic geometry are semicircles that are centered on the x-axis, right? So the perpendicular through here would be, that doesn't look very circular at all, would be part of this semicircle. So let's take, how about I take a point here? How about I take R? Let's call it R1, because I'm going to look at a couple of these. My question is this. My question is, what is the angle of parallelism for this line QS and R1? Well, here's a line that's parallel, right? There's a line through R1 that doesn't intersect QS, so there's a parallel line. So what am I looking at? I'm looking at this angle here. In my mind, in this picture, that's this angle. And of course, that's bigger than 90 degrees. The very nice thing about the upper half plane model is that even though distances aren't the Euclidean distance that you see, the distances happening there in the hyperbolic world are very different than the Euclidean distances you see. The angles, the Euclidean angles that you see are the hyperbolic angles. So the angle between these two lines is indeed this angle that I'm looking at right here, and that's bigger than 90 degrees, right? So of course that's not the angle of parallelism. I know it's somewhere less than 90 degrees. But give me another line that goes through R1 and is parallel to QS. Well, I could take really big circles and cut through it, right? So there's another line, and that gives me a smaller angle. Here's another one. That gives me an even smaller angle. So how small can this angle possibly be? Well, you'll notice that really what I'm looking for is I'm just looking to take sort of this point where they intersect at infinity and take the circle that passes through both of those 2 points. And that would in fact give me the angle of parallelism. Are you following me there? Does that make sense? right? I'm looking at this family of circles. This is sort of the infinite radius circle, but then I'm looking at the family of circles that passes through this point, and I'm taking the point where it meets the boundary here to get closer and closer to here, so they would intersect at infinity. Anything else, any bigger radius circle would or in fact, I guess these are smaller radius circles, would cut through QS. So it's this one right here that gives me the angle of parallelism. Obviously, that's less than 90. I was doing this last night, and then I realized I'm making this way too complicated. Right? This is what I wanted to do. Then I realized I shouldn't look at the angle of parallelism on this side of this line. I should look at the angle of parallelism on this side. Right? So instead of looking over here, I want to look over here. Because it's a lot easier to look on this side. Why is it a whole lot easier to look on this side? Well, okay. What happens if I try to take a smaller angle than this on this side? Well, this is an infinite radius circle. Take any non-infinite radius circle. Take even a really, really, really big radius circle. What's going to happen? It's going to cut through QS, right? So this is indeed the smallest this angle can be on this side, which means that is the angle of parallelism. So just working with these vertical lines, you can actually get the angle of parallelism just by looking on the other side. Which, by the way, you can prove that angle, because angle parallelisms are the same on both sides, that angle is the same as that angle. Certainly kind of looks like it in the picture. So anyway, there's the angle of parallelism. It's obviously less than 90 degrees. Here's what I want to do. I want to look at this line and points that live on this same perpendicular ray, but further away. So how about R2 and R2 and R3? Well, I know how to find the angle of parallelism for a point and a line now in this picture. All I have to do is look at the vertical line that passes through it, and the vertical line that passes through it. And this angle here is my angle of parallelism. By the way, when people talk about angles between these circles and lines or curvilinear things and lines, they're talking about the angle formed by the tangent line to the circle at this point. Right? So the tangent to the circle on the straight line, tangent to the circle on the straight line, and so on. But what is happening? What's happening to these angles of parallelism as I proceed further down this line? They're getting smaller, right? They're getting really, 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 really small. And this isn't just a feature of this model that I've drawn. This is in fact a feature of neutral geometry in general, is that as you progress further down this perpendicular, so you take points that are further away from the line that you started with, the angle of parallelism, well, it's going to stay the same in Euclidean geometry because it never changes, but in general, it decreases in size. Okay, so it's less than or equal to the angle of parallelisms of the points that came before that are closer. So we're going to prove this. This is what I want to do. Because it's sort of insightful as to how angles of parallelism work and how they behave with respect to a line and a point pair, that somehow it depends on how far away you are. So this is in fact, this is 6.2 number 2 in the text. It asks you to prove this. So in the figure below, I'm just going to label everything as they did. In what I've been doing, I've been going with QS and R editors. I shouldn't have been calling this R1. It should have been P. P1, P2, P3, and so on. that was my typical labeling scheme. The textbook actually labels everything slightly differently, so I just go there. In the figure below, if R, then P1, then P2, and angle RP1, Q1 is the angle of parallelism for P1 and line RS and angle R P2 Q2 is the angle of parallelism for P2. For P2 and RS. Then the measure of angle R P2 Q2 is less than or equal to the measure of angle R P1 Q1. All right, so this says that in this picture, if these angles that I've drawn here, R P1 and Q1 and R P2 and Q2, if those are the angles of parallelism for this line pair RS and the points P1 and P2 respectively, if those are the angles of parallelism, then as we just observed, as we progress further down this line, since P2 is further away from R than P1 is, these angles of parallelism are getting smaller. So this angle here is bigger than this angle here. So we're formally proving this observation we just had looking at our model in hyperbolic geometry. How am I going to prove this? Well, as you should be realizing at this point, many of these proofs sort of proceed by contradiction. It's a really common technique. So we'll proceed by contradiction. Suppose that this angle is strictly bigger than this one. All right, so proceed by contradiction. We're going to refer to these angles a lot, so let's give them letter names. How about we say suppose, or let measure of angle R P1 Q1, we'll just call that D1, and measure of angle R P2 Q2, we'll call that D2, whatever those measures are. All right, so this angle here is D1, and this angle here, that's D2. And our assumption here to hopefully reach a contradiction is going to be, let's suppose the opposite. Suppose D1 is bigger than D2. Oh, wait. We're trying to prove D1 is bigger than or equal to D2. Other way around. Suppose D2 is bigger than D1. So suppose as we proceed further down this line, we end up with a bigger angle of parallelism up here. Well, nice thing about real numbers is if I have one real number that's strictly bigger than another one, then I can find another real number that's between them, right? So furthermore, let K be such that D1 is bigger than K, which is less, D1 is less than K, which is less than D2. So I'm just going to squeeze a number between both of them. And what I'm going to do is take an angle up here at P2, take a ray that has angle K. So that's what all this writing is going to be now. So and let Q prime be a point on the same side of P1, P2 of this ray, P1, P2, as Q1 and Q2, such that the measure of R P2 Q prime, measure of that angle equals K. Okay. So here's where I'm actually not telling you just to see the figure. I've written down enough details here. I usually sometimes skip these details and just refer you to the figure. But I've written down enough details that you can reconstruct this on your own without the picture, right? I specifically tell you that Q prime is a point on the same side of this line, P1, P2, as Q1 and Q2. So I know it lies over here. And it's a point so that when I construct this angle, this angle here is angle K. So we'll just call that point Q prime. So what happens? Well, this angle is less than the angle of parallelism, right? It's less than D2, which is the angle of parallelism. So I know it has to intersect RS. It has to intersect somewhere down here. How about I just call that point S prime? So since K is less than D2, the ray P2 Q prime intersects RS, say at point S prime, as we already labeled. Now what happens to this ray? P1, Q1. What happens to this ray? My picture already indicates exactly what happens because this must be what happens. But think of this as a ray. Forget about this picture for a second, right? Forget about the extended part of this. I have a ray that's coming into a triangle, right? It's a ray that comes into a triangle. Pasch's axiom says, okay, this ray came in through this side, RP2. It has to leave, Pasch's axiom says it has to leave either through this side or this side. Right, that was Pasch's axiom. Well, it can't be this side because this is the angle of parallelism. Angle of parallelism means it can't intersect this line RS ever. So by Pasch's axiom, it has to cut through over here, say at a point X. Okay, so now by Pasch's axiom and the fact that D1 is the angle of parallelism, for P1 and RS, it follows that this ray P1Q1 cuts through P2S prime. It follows that the ray P1Q1 intersects P2S prime just a line segment now. The line segment P2S prime at a point X. Yes.
Is it not good enough to just say that since by our assumptions that D1 is less than K, that then if that was intersecting, then that would have to intersect too? So then you have to...
Wait, if so D1 is less than K.
K, which is less than D2, then since K intersects, then D1 would intersect as well.
Since K intersects, well, this is an angle of parallelism for a different point. Oh, since I feel like somehow you'd have to invoke some fact about translating this line down or something and reconstructing this angle down here. I don't.
Okay.
Yeah, I'm not entirely sure. You probably could do something with it, but you'd have to make it work, and there's more than one way to write a proof. So this is the one I'm going with. And in fact, from here I have a couple of ways to proceed. In my notes, I've done something much longer than I realized I need to do. In my notes, I now reach a contradiction by establishing that this is a triangle with an angle sum bigger than 180, which of course violates the Secure-Lejeune theorem. But there's an even more obvious contradiction. How do these relate? K and D1, you just told me, right? K is bigger than D1. Where did we? Here. K is bigger than D1. Can that happen? That violates a really big named theorem that we have. What's the theorem? I have a triangle. What type of angle is this relative to the triangle? It's an exterior, right? It's an exterior angle. Exterior angles have to be bigger than the two remote interior angles. Well, here this says this exterior angle is smaller than this remote interior angle. So we immediately have a contradiction there. So now, angle angle R P1 X, which equals angle R P1 Q Q1. So as you can say congruent. Is an exterior angle of triangle P1X P2 and the measure of angle P1 P2X is bigger than, how would I call it, K. That's bigger than D1, which is the measure of angle R P1X. Contradicting the exterior angle theorem. Yeah, you can also show that, well, this angle plus this angle has to be 180 degrees, so this angle plus this angle, if K is bigger than D1, this angle plus this angle is bigger than 180 degrees, so this triangle is bigger than 180. So there's another immediate contradiction. But how did we achieve this contradiction? We achieved this contradiction by assuming that D1 was bigger than, or sorry, was less than D2. So therefore, D1 is bigger than or equal to D2. And we're done. That took much longer than I thought it would. But we're there, and I think it's an interesting fact. One, it reminds you that angles of parallelism are not something that's sort of defined for your geometry. It's not a fixed number. It depends on the line and the point you take. And in general, sort of the further away you get from the line, your angle of parallelism is shrinking. It's strictly shrinking in hyperbolic geometry, as we saw, and in Euclidean geometry, it's sort of staying the same all the time. But these homework problems, just to mention them very, very quickly. I guess I don't have time to write anything down. But number 9. So number 9, 3.6, number 9. It's just a Sakiri quadrilateral with a whole bunch of triangles drawn in it, and you're asked to prove congruence between two line segments. The way you proceed here is you just do a whole bunch of triangle congruence chasing, right? So you know lots of things in the picture already. It looks like this. You're told it's a Sakiri quadrilateral. So in particular, I know those two sides are congruent. You've got these two diagonals. You've got the point of intersection, and then this asks you to come halfway along to M and N. And because you're coming halfway along, I know that those are congruent, and those are congruent because it cuts it down the middle. And there's other things you can draw from this picture. For example, vertical angles tell me those angles are congruent. We know because it's a Sakiri quadrilateral that the two summit angles are congruent, so there's something you can already assume. And you immediately can do other things. For example, if I look at this triangle here and this triangle here, they agree on side, angle, side. So immediately you have that these two diagonals are congruent to each other. and moreover, not just the sum of angles, but this angle here and this angle here are congruent. So eventually the goal is to show that these two line segments are the same length. It's just a whole bunch of SAS, triangle chasing. Eventually you can show by congruence of enough things that these two line segments have to have the same length, right? So I won't lay out the details for you. I'll let you chase the triangles there. 22 says prove an interesting result if the sum of the angles of every triangle is a constant n, then n must be 180, and therefore the geometry is Euclidean. So we know in Euclidean geometry, triangle sum of every triangle is 180. This says something a bit stronger. It says if every triangle has the same angle sum, so this establishes that in hyperbolic geometry you must have triangles with different angle sums. If every triangle has the same angle sum, n, then n must be 180. A really easy trick to this one, just take a triangle and cut it into two triangles. And then look at the angle sum of those two triangles compared to the original. And you'll get an equation that eventually allows you to say n is 180. All right, so that one's not so bad. And then the last two were not intended to be long proofs at all. Next one says you have a Securi quadrilateral. So Securi quadrilateral. That's also Lambert. What does Lambert mean? Lambert means I've got a quadrilateral with three right angles. What you want to prove is that this must be a rectangle. Well, actually it's almost immediate. Again, this is not intended to be a hard proof. Why must that be a right angle? Well, because for Securi quadrilaterals, what do we know about the sum of angles? They're congruent, right? So if this is 90, this one must be as well. So not much to do there, just write down the details of that. I'll actually use that in a proof that we do next time. So I'll use that fact. And we're just about out of time here, but last but not least, again, 28, not intended to be a long proof. If one rectangle exists, then prove that the geometry is Euclidean. In other words, prove that Euclid's fifth postulate is true. So if a rectangle exists, prove that Euclid's fifth postulate is true. This isn't intended to be a proof by construction or anything. You're not constructing anything here. All you have to do is piece results together. All right, so look back at the theorems we've proven. If a rectangle exists, then what else is true? All right, well, if a rectangle exists, and we've proven that if one rectangle exists, then every triangle has an angle sum of 180. Right? So then look through your results. If a triangle has an angle sum of 180, what does that imply? What have we proven that's equivalent to? And so on. And eventually just construct a string of theorems that tells you if a rectangle exists, then Euclid's fifth postulate is true. That's all I'm looking for there. And that's all four of them, so it shouldn't be too bad. Well, we'll stop here.